Okay, welcome to our second Cyber Day lesson. I want to pick up with the problem we all left off with in class yesterday, which is problem 20 in your packet in section 10-1. Okay, various classes got various distances through this problem, so I'm going to start it from the beginning. Feel free to fast forward a little bit if your class covered most of it. But there is an important point that comes with this problem at the end. A grinding wheel with a radius of 20 centimeters is rotated at a speed of 200 RPM. When the power is cut off, it slows to a stop in 90 seconds. Okay, so we know the initial, this is number 20, we know the initial angular velocity is 200 RPMs. We know it slows to a stop, so the final angular velocity is 0. And we know it does this in a time of 90 seconds. This grinding wheel has a radius of 20 centimeters. And we're really, if you read down here, we're asked about two different points of the problem. It says, what is the angular displacement of a point located at 1/2 the radius? And this is the typo. What is the angular displacement of a point located at the radius? So I'm going to call this point A, that's half the radius, and this point out here B, at the full radius. Okay, so if we're going through the thought process, we're asked for angular displacement. The symbol for angular displacement is delta theta. If you don't have an initial position and a final position where you can subtract, the only other way you know of in section 10-1 to find angular displacement is to use the definition of average angular velocity, which is omega equals delta theta over delta t. The average angular velocity multiplied by the time will give you the angular displacement. If we look at the initial information given in the problem, we're given the initial angular velocity and the final angular velocity. You will recall that when this omega is written with a bar over it, that's the average angular velocity. Neither of these represent the average value. Now I'm going to do this a little bit in a different order than I did in class. But if you have an initial velocity of 200 RPM and a final velocity of 0 RPM, and you're slowing down at a steady rate, the average angular velocity would be 100 RPM. But before you plug this directly into here, you have a problem. RPM is not the official unit for angular speed. Angular speed is supposed to be measured in radians per second. So before you can go any further, you need to convert RPM for radians per second. Yesterday when I did it in class, I started off by converting the 200 RPMs into radians per second. You can do it either way, as long as you eventually get to radians per second. So 100 rotations per minute. Rotations per minute is rotation over a minute. In one rotation, you have 2 pi radians. And in 1 minute, you have 60 seconds. When you do the math, this works out to be 10.47 radians per second. And that's your average angular speed. And this is what we're going to plug in right there. So 10.47 radians per second. We slow down over a time of 90 seconds, so you multiply that by 90, and you get an angular velocity of 942, not angular velocity, excuse me, an angular displacement of 942 radians per second. Or excuse me, 942 radians. I keep wanting to make this a velocity. Sorry. Okay, now the question asked, what is the angular displacement of a point located at 1/2 the radius? That is what I'm calling point A. There's nothing about what we just did that specifies the angular displacement for a particular location. And there's a reason for that. If we think about point A as this thing spins and the angle it would sweep out, and we think about point B as it spins and the angle it would sweep out, those are the same angle. If you go rotate this wheel through a quarter turn, both point A and point B would rotate through 90 degrees. So this answer we found for the angular displacement of 942 radians, that is the angular displacement of A, and it is also the angular displacement of B. Both points A and B rotate through the same angle. Okay. Now C asks, through what linear distance will a point at 1/2 the radius travel? And D asks, through what linear distance will a point at the full radius travel? Now you can see by looking at my diagram here, while they go through the same angle, about 90 degrees for what I've drawn here, they go vastly different distances to get there. So we're going to get a difference in our answers for C and D. We're being asked to find the linear distance the point travels through. That linear distance is a curve. You can think of it as part of an arc. And in fact, we have a way of finding arc length. Our formula for arc length is S equals R theta. So if I want to find the arc length for A, I'm going to use the radius at point A and multiply it by the theta, or the angle at which it moves through. The radius, well, the full radius is 20 centimeters. To point A, the radius is going to be only 10 centimeters, or 0.1 meters. It moves through 942 radians. Now, my drawing up here is just a representation. In reality, guys, we know that one rotation is 2 pi radians, which is about 6.28. So when we say something moves through 942 radians, it's going a lot further than this. In fact, it's going completely around multiple times. That being said, we can still find the total distance A moves through as it goes around multiple times. When we do the math for point A, we get 94.2 meters. Let's look at point B. It's going to be the same basic calculation. The arc length for B equals the radius for B times theta. B is the full radius away, so 0.2 meters. The angle, 942 radians. The arc length for B ends up being 188.4 meters. Okay? There is a part E to this problem. Before it's cut off, what is the period of one rotation? Okay, the period of one rotation before it's cut off. So, different situation. Before it's cut off, it was spinning at 200 RPMs. So it had an initial angular speed of 200 RPMs. When you convert that to radians per second, that's 20.94 radians per second. And the question is, if you're going that fast, what is the period of one revolution? One revolution is an angle measurement. So our angular displacement is one revolution. It might be better to think of that in terms of radians, which would be 2 pi radians. We know the angular velocity equals the angular displacement divided by the time. That's our definition for average angular velocity. Before we cut the grinding wheel off, our angular velocity was constant. If we take and rearrange this formula, delta t would be delta theta divided by our average angular velocity. If the angular velocity is constant, which it is before we cut it off, the average angular velocity is just the value for the angular velocity. So I can take 2 pi, I can divide by omega, 20.94 radians per second. When I do the math, I get 0.30 seconds. And since that's the time to go around one time, we're going to call that the period. Okay, let's continue. So if we turn the page, example 31 asks, what can be said about linear and rotational quantities with relation to the radius on a rigid rotating object? Guys, that is what we had in the previous problem. This was a rigid rotating object, a grinding wheel, and the rotational quantity we looked at was the angular displacement. And what we found was that no matter how far you are away from the center, no matter what the radius is to the point, the angular quantities had the same value. However, when we tried to find the linear distance these points moved through, we found they had different values for their linear distance. So if I want to summarize this, for a rigid rotating object, angular quantities for any 2 points are the same. Linear quantities, like arc length, depend on the radius value. Okay, 22. If the angular velocity of a rotating object increases or decreases with time, so if our angular velocity is changing, we say the wheel experiences an angular acceleration. The symbol for angular acceleration is the Greek letter alpha. Okay? It's kind of like the Christian fish symbol, but it's curved on the front, not pointed. The average angular acceleration is the change in angular velocity divided by the change in time. In the space flow, write the formula for this quantity. That's terrible. Average angular acceleration is the change in angular velocity over the change in time. Omega final minus omega initial. Okay. The SI unit for angular acceleration is radian per second squared. And you can see that in the formula. You'd have a radian per second on top with the angular velocity. When you divide by time, the time would be in seconds, which gives you a squared unit of time on bottom. Number 24. When the time interval approaches 0, the average angular acceleration becomes the instantaneous angular acceleration. As is our custom from this point forward when we discuss angular acceleration, unless specifically stated otherwise, we are referring to the instantaneous value. We always specify average whatever. Okay, if we just say angular acceleration, we're talking about an instantaneous value of it. An angular acceleration that makes the angular velocity more positive is considered to be a positive angular acceleration. Okay, then we're asked to consider these diagrams. In my first diagram, we have an angular acceleration alpha that's greater than 0. We have an omega greater than 0. That's to say both alpha and omega are positive. And the angular speed will increase over time. Okay, my next picture. Okay, my next picture. I have an angular velocity omega less than 0, so that makes it negative. I have an alpha less than 0. That makes it negative. Okay, here too the angular speed increases. Guys, notice in this picture what's happening. The wheel is spinning to the right, and we have a rope tied to the wheel with a weight that's exerting a downward force on one side of the pulley that's going to want to cause the pulley to speed up as it turns to the right, or turns, I should say, as it turns clockwise. Look at this picture right here. Things change up. Omega is greater than 0. That is, omega, my bad, is less than 0. Omega's negative. The pulley itself is spinning clockwise. That makes for a negative angular velocity. But my angular acceleration is positive. Okay? And you can tell, so the pulley, the weight is trying to make the pulley spin the other direction. That's going to cause the angular speed to decrease over time. And my last situation over here, I have an omega, the angular speed, greater than 0. That means it's positive, so it's rotating counterclockwise, but I have an angular acceleration alpha less than 0, which means the hanging weight is trying to make it rotate counterclockwise. And in this case, the angular speed will decrease. 27 asks, write a general rule for the sign of the angular velocity and acceleration that describes whether the angular speed will increase versus decrease. Really simple. You can expect angular speed to increase when alpha and omega have the same sign. It doesn't make a difference if they're both positive or they're both negative. If alpha and omega have the same sign, the angular speed will increase. Angular speed will decrease when alpha and omega have opposite signs. Guys, if you recall, this is exactly the way linear velocity and linear acceleration works. When the signs are the same, things speed up. When the signs are opposite, things slow down. Okay, let's look at example 28. In example 28, we're asked to determine the angular acceleration of an old-fashioned phonograph record player if it takes 10 seconds to get up to its operating speed of 33 1/3 RPM. Express your answer in SI units. So that means not only do we want alpha, but we want it in radians per second squared. Okay? It takes 10 seconds to get up to an operating speed, so that would be omega, of 33 1/3. So that's 33.3, whatever, radians per second. Presumably, if we're getting up to this speed, we started with an initial velocity of 0. Our formula for angular acceleration is change in angular velocity over change in time, omega minus omega naught over t. We're getting up to 33 1/3 radians per second. We're starting at 0. We do this in a time of 10 seconds. 33 divided by 10 gives me, oh goodness, I made a huge mistake, didn't I? It was 33 1/3 RPM, not radians per second. That's what I needed, but that's not what they gave me. So the first thing we have to do is to take our 33 1/3 RPMs and convert it to radians per second. So 33 1/3 rotations per minute. One rotation is 2 pi radians. And in a minute, we have 60 seconds. When you do the conversion, you get 3.49 radians per second. So alpha will be your final angular speed, omega, in radians per second, which is 3.49 radians per second. Take away 0 from that, divide by 10, and alpha is 0.349 radians per second. You got to be extra careful with those angular velocities given in RPMs. Before you can do anything, you have to convert to radians per second. Okay, let's slide over and look at section 10-2. 10-2 says, is the start of rotational kinematics. You'll remember kinematics is the branch of physics that describes motion. So rotational kinematics will describe motion. Now the beautiful thing here is everything we've done in linear motion carries over to rotational motion if you know what are known as the rotational analogs. That is, every linear quantity has a rotational counterpart. So, like for position, the rotational counterpart for position is theta, and the unit will be radians. Displacement, the rotational counterpart of displacement is the change in theta, or delta theta, and it has a unit of radians. The rotational counterpart of velocity is angular velocity, omega, and it has a unit of radians per second. The rotational counterpart of acceleration is angular acceleration, alpha, and it has a rotational counterpart of radians per second squared. And time is just time, no change. Okay. Any of our kinematic equations can be rewritten in terms of angular or rotational quantities. Beside each of the linear kinematic equations below, write the corresponding kinematic equation in terms of rotational quantities. So here are 4 basic kinematic equations that we've been using all year. And now let's make them look a little bit more complicated. So displacement. Displacement's delta theta. So delta theta equals 1/2. Instead of writing V naught, velocity is omega, so we'll write omega naught plus omega final times time. How about V equals V naught plus AT? Well, the counterpart of velocity is omega, so omega equals omega naught plus acceleration. Acceleration, the rotational counterpart is alpha. How about this one? V squared equals V naught squared plus 2AD. That would be omega squared equals omega naught squared plus 2 alpha delta theta. Sounds like you just joined a fraternity or something. Alpha delta theta. But anyway. And the last one. D equals V naught T plus 1/2 AT squared. That's delta theta equals omega naught T plus 1/2 alpha times T squared. You will remember that, like the kinematic equation, that the kinematic equations are only valid when the acceleration is constant. Likewise, the rotational kinematic equations are only valid when the angular acceleration is constant. Okay, I'm going to work 2 example problems and this will be the end of the video. So, number 5. A rope is wrapped around the edge of a wheel that is initially at rest on an axle. Initially at rest, omega naught equals 0. When the rope is pulled with a constant force, the wheel accelerates at 2 radians per second squared. Alpha, 2 radians per second squared. How long, so what is the time, for the wheel to complete 1 rotation? Now, 1 rotation, that is the angular displacement. Delta theta equals 1 rotation, which is also 2 pi radians when we want to think in terms of SI units. So how long to complete 1 rotation, and what will be the rotational speed at that time? So how long and how fast are we turning at that time? Okay, so if I just look at, well, here's what I recommend. These symbols aren't very familiar to you yet. You might want to think in terms of the linear quantities. Omega naught is like V naught. Alpha is like A, T is T, delta theta is D. Most you can recognize the equation that relates V naught, acceleration, time, and displacement.